Hey guys, in this video, I want to talk to you about acid-base and the crash course, putting it all together. So to start off, we want to talk about the Bronsted-Lowry definition. And the Bronsted-Lowry definition is what we use for AP. Now there is also a definition for your for Arrhenius. There's also a definition for Lewis. However, AP, we only stick with Bronsted-Lowry. So the definition, an acid donates a proton. A proton is essentially an H plus little ion there. The base accepts the proton, and then you also have things that can act as both an acid and a base. So if it can act as an acid or a base, we call that amphiprotic or amphoteric. You also have to know some terminology with conjugate acid and conjugate base. A conjugate acid is the product that's formed once the base has accepted the H+. So it's your product, then once the base has accepted the H+, it's what it turns into. Your conjugate base is the product that's formed once the acid has donated an H+. So what I did here is I gave you an example. You have HF plus H2O yields H3O plus F minus. So in here you see that HF is donating a proton, so therefore it's the acid. H2O is accepting that proton, so it's acting as the base. And then as a result, the acid, once it has donated the proton, turns into the conjugate base. And the base, once it has accepted that proton, turns into the conjugate acid. So they like to ask sometimes your conjugate acid-base pairs. One pair would be HF, which is the acid, and F minus, which is the conjugate base. And another pair would be H2O, which is the base, and H3O plus, which is the conjugate acid. There's another thing that they like to ask, tying in your K value. So if they give you a K value that's greater than 1, then that means that the products are favored. So what that means is that the reaction's going to the products, is making products. In order for that to happen, these reactants, the acid and the base on the reactant side, has to be stronger than the acid and the base that you see on the product side. When we say stronger, we just mean it more readily dissociates, right? More readily dissociates. So that means it's easier for this to transition the proton than it is here. And as a result, my reaction is going to the products. If K is less than 1, the opposite is true. My reactants are favored. That means my reaction's going to the reactants. So therefore, my products are more easily dissociated, which means they're a stronger acid and base than the other. As for acid-base reactions, there's really two main reactions that you'll have to be able to write. The first is the acid dissociation reactions. So this just shows you that you can write it both ways, one without water and one with water. What I want you to realize is that an H plus and an H3O plus means the same thing. H3O plus is just what you write when you're including water in the reaction. If you're not including water in the reaction, it's just H plus. So this is an acid dissociation reaction. We're just putting that that acid into water and seeing what happens. But then you have acid-base neutralization reactions. These follow the A plus B yields Ca plus Cb. This means acid plus base yields conjugate acid plus conjugate base. So when I write the reaction, most of them you can treat them like a double displacement reaction where you're basically switching partners. So you see you have sodium and acetate's going to come together, and you have H and OH coming together to form water. Now do remember you have to write net ionic equations here. So we have to pay attention to our solubility rules. Referring to solubility rules, remember that strong acids and bases are classified as soluble. So from there we can pick out our spectators. Remember, if we write our net ionic equation without the spectators, we have to write those things as ions. The NH3 formula doesn't really follow the double displacement kind of reaction, but it does follow what an acid and what a base does. So this is the acid. It's donating the proton to make NH4+, and then you have your conjugate base left over here. Cl- is an ion here. because it's a strong acid here, it's going to dissociate and become an ion, so therefore it's a spectator. So this is your net ionic equation for this particular reaction. On to the next page, we have strong acids and strong bases. So these are the list of strong acids and strong bases you need to know. You need to have that memorized. Strong acids and bases dissociate 100%. They have large Ka or Kb values. And what's important about these is that whatever the concentration of the strong acid or strong base that you have, that is exactly equal to the concentration of the H3O plus or the OH concentration. So if I have a strong acid, its concentration is equal to H3O plus concentration. If I have a strong base, its concentration is equal to the OH concentration. After that, once I know these two concentrations, I can either find the pH or the pOH accordingly. So I can directly plug these concentrations into these formulas for strong acids and strong bases. For weak acids and weak bases, however, I cannot do that. The reason why is because they only dissociate around 1 to 3%. So they have small Ka and Kb values. Conceptually, as the Ka value increases, the strength of the acid increases, and therefore the strength of the conjugate base decreases. So acid, conjugate base are inversely related. Base and conjugate acid is also inversely related as far as strength goes. So as the Kb value increases, the strength of the base increases, but the strength of the conjugate acid decreases. So, like I said, weak acids and bases have small Ka and Kb values. So this is just a generic form to write the Ka and Kb expressions. And you'll see this on your equation sheet as well. If I want to figure out the pH of a weak acid or weak base, I can't directly plug that concentration in because it's not 100% dissociation. So I have to follow these steps. First, write the weak acid, weak base dissociating in water. So you're writing that reaction. This first reaction is an acid dissociating in water. This second reaction is the base. The second thing is I set up my Rice chart. So that's where I have the concentration. Remember, water is never included. You have 0 of both of these, plus X, and go from there. Once you set up your Rice chart, you can plug that into your K expression. Remember to use Ka for acids, Kb for bases. The next thing is you solve for X. Now, if I'm working with acids, X is equal to the H3O plus concentration, and then I can plug it into the pH formula. If I'm working with bases, the X is equal to OH concentration, so I have to plug it into the pOH formula first, and then find the pH from there. And those equations are the exact same equations as I see here for strong acids and strong bases. Another thing, if I have a Ka but I need a Kb or vice versa, I can use the Kw formula. So Kw is equal to 1 times 10 to the negative 14. That value is equal to Ka times Kb. There's another thing here. This is especially what they ask for acids. They could ask this on multiple choice or free response. They will give you a percent dissociation, or you'll have to find a percent dissociation. The way that we find that is the H3O plus concentration over the acid concentration times 100. So here's where I find these values. H3O plus concentration is found by doing 1 through 4 right here. You're solving for X. The HA concentration is what's given to me at the beginning of the problem. So that's how I calculate percent dissociation. Next up, we have mental math. So if I have an H3O plus concentration, and that value is 1 times 10 to the negative 6, pH is log based, so that means it's 10 based. So I take this exponent, and that's equal to my pH. But that's only if there's a 1 in front of this here. You see how for the second example, you have a 3. So as that number gets greater than 1, what's happening is your pH is approaching the lower number. So instead of your pH being 6, it's now approaching 5. So all you have to do in order to answer a multiple choice question is say, if this number is greater than 1, the number for the pH is between 5 and 6. So it's between the number below this exponent here and that exponent. If I want to do the opposite and figure out my H3O plus concentration, if it's an exact value, so pH of 3, I plug that in as my exponent. But if I have a decimal here, then I'm going to plug the number above this number in front of the decimal as my exponent. So it's going to be some number times 10 to the negative fourth. Oxyacids. So oxyacids are acids that have an oxygen on them. The concept here is that you have some oxyacids that are weaks and only a few oxyacids that are actually strong. You have to justify why. This will mainly be free response. They could ask a few conceptual questions on multiple choice as well. So here's the main idea. As the number of oxygens increase, the strength of the acid increases. But we cannot just say that on the free response. We have to understand and justify why. So this is what you need to include. Since oxygen is electronegative, an increase in the number of oxygens will increase electron density. So what that means is basically oxygen is an electron hog. So it's like pulling all of the electrons closer to itself. And so when we say it's increasing electron density, what it's doing is it's hoarding all of those electrons in one place. As a result, it leaves the OH bond weak. Now, if there's a weak bond, less energy is required to break that bond, and so that means that the acid dissociates more readily. So this is, if the acid dissociates more readily, that means you have a stronger acid. So again, this is the explanation for oxyacids, why one acid might be stronger than the other. Now we're into our big concept here, buffers. What a buffer does is resist a change in pH. What a buffer consists of is a weak acid with a basic salt. A basic salt is also known as a conjugate base. Or you have a weak base with an acidic salt, and an acidic salt is also known as a conjugate acid. When you're reading free response questions, one kind of thing to help you is you're looking for ic and ate. So for example, you have acetic acid, that's where the ic is, and sodium acetate. So the 8. So when you see both of those present in a free response question, if you recognize the ic and 8 kind of combination, then you know that you have a buffer there. You have acidic buffers, you have basic buffers. It's all depending on whether or not you have a weak acid or a weak base listed there. So this would be a basic buffer because it's a weak base with an acidic salt. This would be an acidic buffer because it's a weak acid with a basic salt. Conceptually, what's happening whenever we add strong acid or strong base to a buffer? How does a buffer work? Well, you have both components. You have an acid component and a base component. The acid component of the buffer neutralizes any addition of strong base. So if I add strong base here, this acid will be the one to react with that. As a result, the acid and the strong base will form some of this A- here. And you'll see your pH actually increase a little bit. If I have a strong acid that I'm adding into my buffer, the conjugate base is the one that's going to neutralize it. So conjugate base is going to react with my strong acid, and as a result, it's going to make more of this HA. As a result, my pH should decrease just a little bit, but it's still resisting a major change in pH. The best buffer ratio is a 1-to-1 ratio of weak acid to conjugate base. So you want just as many of these as you have these. Also, you can increase buffer capacity by increasing the amount of HA and A- in a 1-to-1 ratio. So if I have more of that stuff there, then I increase buffer capacity. As long as you maintain it in the 1-to-1 ratio, your pH does not change. The reason why is because if you look at the pH formula, your A- concentration is going up, but your HA concentration is also going up by the same amount, so therefore that ratio doesn't change. If that ratio doesn't change, then pH does not change. In order to make a buffer, there's two ways, and it's based upon what you are given. So if you are given both components of the buffer, so that means you have the acid and the base part, what you're going to do is mix a 1-to-1 ratio of the weak acid to the conjugate base, or if you have a weak base and a conjugate acid, you're going to mix those in that 1-to-1 ratio in enough water to dissolve the salt. That is if you have both components of the buffer on hand. But if they tell you that you only have one of the components, so you either have the acid component or the base component, what they'll also say in the question is that you also have strong acid or strong base available. So what you're going to do is you're going to add strong acid to the base or add strong base to the acid until you reach the desired pH. The reason why you want to do this is because if you have the base and you add strong acid to that, that will make the acid component of the buffer. If you have acid and you add strong base to that, you will make the base component of the buffer. So you're basically reacting these so you can make the other half. In order to pick buffer components, you first have to make sure that you choose the correct weak acid or weak base. To do that, you choose the pKa of the weak acid or weak base, and that has to equal the pH desired of your buffer. Then you choose the correct conjugate acid or conjugate base accordingly. So for example, if I chose H2PO4- by matching up its pKa to the pH desired, that's going to be my weak acid. My conjugate base is just minus an H plus from there. So it would be this guy right here. You see how that and that, this is my acid, this is my conjugate base to that. Opposite if it's a weak base conjugate acid. So you would choose your weak base, and then your conjugate acid would just be an H plus attached onto it. To find pH of buffers, that is your equation that you see there. pH equals pKa plus log of A minus over HA. Base is A minus, acid is HA. pKa is saying negative log of your Ka value. So this is if I just have a buffer sitting around, I'm not adding anything to it, I just directly use this equation. But if I'm adding an invader, so an invader is a strong acid or strong base, you first have to write your reaction. If it's a strong acid if it's a strong acid that you're adding, this is your reaction. If this is a strong base that you're adding, this is your reaction. This is like the conceptual thing we were talking about earlier. Then you set up your Rice chart. Your strong acid or your strong base is always going to be your limiting reactant. So you're basically, if this is my reaction, I subtract all of my strong acid, subtract the strong acid from here, add the strong acid to here. Strong base, I subtract all of the strong base, subtract the strong base from here, add the strong base to here. Don't forget, if I am mixing volumes, so if I'm mixing molarities and volumes, I have to do M1V1 equals M2V2 before I plug it into my Rice chart. After I find those new concentrations from my Rice chart, I then just plug it into this buffer formula here. The next thing we're going to talk about is salts. Now, salts are conjugate acids or conjugate bases. They are ionic compounds. And I know I've said this over and over again. An ionic compound is a metal plus a nonmetal, a metal plus a polyatomic ion, or a polyatomic ion plus a nonmetal. So you have to be able to identify those. Here are some examples of some salts. So I have a basic salt here, an acidic salt here, and a neutral salt here. Basic salts are conjugate bases. They have a pH greater than 7. Acidic salts are conjugate acids. They have a pH less than 7. And neutral salts have a pH equal to 7. How I figure out if a salt is acidic, basic, or neutral is I break it up into its components. So I look at the base component, I look at the acid component, and whichever is strong supersedes, kind of like a tug of war kind of match. If both of them are strong, then that means that we have a neutral salt there. We also have to be able to write our hydrolysis reactions. It's basically the neutralization reaction in reverse. So you just take your salt, react it with water, and you treat it like a double displacement reaction. So it's the opposite, it's the reverse reaction of a neutralization reaction here. So I showed you an example of this basic salt, and I showed you an example of an acidic salt. One thing I do want to point out, NH4OH sometimes is, the best way to explain it is it's basically not stable by itself, so it will break down to make NH3. So you could see this written in this form, or you could see it written in that form. To figure out the pH of salts, we first have to write our hydrolysis reaction. We then have to set up our Rice chart to solve for X. X for acids will be H3O plus. X for bases will be OH minuses. And don't forget, I have to use a Ka value for acids and a Kb value for bases. After I figure out those concentrations, I plug them into the pH or pOH equations. So you see that this is very similar to how we take the pH of weak acids and weak bases, because that's basically what salts are, weak acids and weak bases. The next idea is titrations. Okay, so you have your analyte, which is in your beaker, you have your indicator that goes in your beaker, and you have your titrant that goes in your burette. Make sure that your titrant is standardized. That means that we know its molarity. For indicators, you have the endpoint, which is the color change. The equivalence point is when the moles of the analyte at the beginning of the titration is equal to the salt created. So whatever I started with at the beginning of my analyte, that has totally converted to my salt. That is what's happening at the equivalence point. Now, if you choose the correct indicator, the endpoint and the equivalence point will happen at the same time. So you will get that color change at the equivalence point. So in order to choose the correct indicator, the pH at the equivalence point needs to be equal to the pKa of the indicator. I feel like we're pretty good on titration curves. We've been doing a lot of practice. So this is a weak acid, strong base titration curve. This is a weak base, strong acid titration curve. You see here all the different points, and you have your graphic organizer that goes along with this as well. So you have before the titration, before the midpoint, midpoint, after the midpoint, equivalence point, after the equivalence point. So what's present here before the titration is just your weak acid. Then I start making my buffer in this region here. So I have more weak acid than conjugate base, but at the midpoint, those are equal. After the midpoint, I have more conjugate base than I do my acid. At the equivalence point, remember that all of this stuff has been converted to my conjugate base, which is my salt. After the equivalence point, we have some conjugate base there because that hasn't gone away, but we also have some OHs floating around. Notice that the weak base, strong acid titration curve is similar, except for you're working with weak base, going to conjugate acid, and all that good stuff. Here you have some H pluses floating around instead of here OHs. So make sure that you guys know the parts of the titration curve. Couple of important things along the titration curve. So your midpoint is the optimum buffer ratio, which is again 1:1. This is because your weak acid is equal to your conjugate base, or your weak base is equal to your conjugate acid. Midpoint is found at half the volume of the equivalence point. And a very important thing here, pH is equal to pKa of your analyte. The reason why is because if these two in your buffer equation are equal, this whole thing is 0. So pH equals pKa. Now remember that this is of my analyte that my pKa is equal to. At the equivalence point, all of your weak acid or weak base has converted to conjugate acid or conjugate base. So if it's a weak acid, all of that weak acid has converted to conjugate base. If it's a weak base, all of that has converted to conjugate acid. Also, if your titrant and your analyte is a 1:1 ratio, and where I find that is from the mole-to-mole ratio from the balanced equation, if it is a mole-to-mole 1:1 ratio, then the moles of the analyte is equal to the moles of the titrate there. One important thing that you'll have to be able to do is find the equivalence point volume. This will help you for the sketching titration curves. It will also help you whenever you're having to do a titration calculation to figure out where you are at along the curve. So what I do is I take the molarity of the analyte times the volume, make sure that is in liters of the analyte, and that's equal to moles of the analyte. Then I take those moles. So here I am, I take those moles, do a mole-to-mole ratio. That mole-to-mole ratio is coming from your balanced equation. Most of them will be 1-to-1, but not all of them. Then that will give you moles of your titrant. If I know moles of my titrant, I can plug it in here, because I will more than likely be given the molarity of my titrant, and I'm solving for this volume in liters. So that is how I find my equivalence point volume. Last but not least, sketching titration curves. So anytime you have to sketch a titration curve for a free response question, make sure you include the following: the beginning pH, that's of my analyte; the ending pH, that's of my titrant; the pH at the equivalence point. Now, all of these can be rough ranges, all right? It has to be in the proper range. So weak acid, weak base, strong acid, strong base range. Same thing for the ending pH. The pH at the equivalence point, if it's a weak acid with strong base, titration, it has to be greater than 7. Weak base with strong, I don't know what I just said. Let me rephrase that. Weak acid with strong base, pH at equivalence points greater than 7. Weak base with strong acid, my pH at equivalence point is less than 7. And if they're both strong, then the equivalence point is exactly 7. Okay, so make sure all these three things are in the proper range. What you do have to calculate to get an exact value of is the volume of the equivalence point. So make sure you find that exact value when you're sketching that titration curve. This is where you get your points. So I just breezed through this crash course. I hope this helps you. If you have any questions, ask me in class. Toodaloo.